Hey everyone, um, I'm back for another video. Um, Before I start, um, I emailed out all the homework twos. You guys did really well. I also posted um, solutions on Teams, and but I'd be more than happy to address any questions you guys have. Um, I may put a comment on Teams just asking if there's any interest in having any sort of a Q&A about any material or homework problems. I did put comments on a lot of the homeworks pointing out if any mistakes were made. So there should be good feedback there. But as much as you guys need, I want to be here, be available to you. So just let me know. Be happy to do that. I'll be well. You guys have homework 3 to work on, and probably won't post another homework set until maybe another chapter or another lecture to so we can get a couple more chapters to cover. But we will be within the next week or so winding down Callister and getting to the end of it. And this is the end of week 3 already. Hard to believe. According to the syllabus, I am a day behind, but actually for ceramic materials, which is what we'll be talking about in this video, I'm going to combine chapters 12 and 13 into one video. So I'm hoping to still keep it within the 50-minute or so time frame, but we'll cover basically 2 lectures worth of material, and the notes are not or about the length of one lecture. So I think it will work, and I think we can do that for a couple of reasons. One is that as compared to metals, ceramics are not as big of a emphasis item within the Air Force, especially for aerospace materials. That may be changing as hypersonics come online, but our legacy systems are metals dominated. The second is that I think we can save some time because a lot of the material will be presented in the context of ceramics, but very similar manner to what we've already discussed for metals. You'll see a lot of the similarities in structure and bonding and crystal structures, also mechanical properties, and so a lot of it will be compared and contrasted to the metals, but we've laid a lot of that foundational groundwork. So I will not take up too much time here. Let's go ahead and switch over and start talking about ceramic materials. All right. So for ceramic materials, let's start at the beginning like we did with metals, with the bonding. So if we remember, different class of materials, different type of bond. Here we're talking about covalent and ionic bonding. Remember that covalent ionic bonding is not mutually exclusive, right? There's a spectrum where we go from fully covalent in the carbon-carbon bonding or silicon bonding, or basically any group 4 atom would be purely covalent, all the way to maybe not pure ionic, but as highly ionic as we can get, say with say fluorine bearing crystal structures where we have a really electronegative atom, really hogging a lot of electron density. And since mostly in ceramic materials, right, most of our bonds have at least some ionic character, the bonding can be thought of as primarily ionic, which adds in an additional factor that we'll talk about when we talk about crystal structure, and that is charge neutrality. We also, because we have ions, we also tend to have a more dramatic difference in ion size, right? So not only do we have to worry about charge neutrality, and we have multiple types of atoms, but they can vary quite a bit in ion size. and this is exacerbated if we remember when we form ions, right? Because um, when you're forming, say, a negative ion, right, you are gaining an electron, and that electron goes into a shell that is furthest away from the nucleus. And so you get an electron, but you do not get an additional proton. And so that electron is not pulled in as tightly because there is one less proton in the nucleus, right? And so ions, negative ions, tend to be bigger because we're adding electrons. We're not adding protons, so they expand. Conversely, cations, right, or positive ions tend to be smaller because you have one less electron, right? So not only is that electron being taken out of the outer shell, which in some cases could actually remove that shell from the atom completely, um, but we have one less electron and we actually have an extra proton. So opposite to what we see in the negative ions, we actually see the electron density being pulled inward, right? So those contrasting cases give us much larger negative ions than positive ions or anions or cations. Um, and so this helps to determine the crystal structure. If we come over here to the right side and we look at various crystal structures, coordination geometries, kind of ways of arranging different sized anions and cations, right, we see that by nature of their relative sizes, that dictates how they can fit together. If you recall with metals, we had a common crystal structure of FCC, HCP, to a lesser extent BCC, because the metallic bonds were non-directional and there was no charge neutrality to be had, and so the one governing factor was just packing these atoms in as tightly as possible. Here we have charge neutrality, right? So we have to have a fixed ratio between anions and cations to maintain charge neutrality. And so we're trying to pack these in as densely as possible, but we have to have equal numbers of anions and cations. Well, we have to have the same ratio at least. And as they're packing in, right, we have these very different sizes. And so depending on the ratio of cation to anion, that dictates how they're going to pack together most efficiently, right? So for instance, if you have a relatively small cation, right, it might fit in the interstitial space between close packed anions, right? You're going to have some space in there, and if the ion's small enough, it can fit. As the cation gets larger relative to the anion, right, you're shifting to crystal structures that have a higher coordination number. And it takes, the space in between these atoms needs to be larger, and that enables the cation to reach out and touch more anions, right? So for instance, by the time you get to, say a half to a 3/4 or so, now the space required is going to require a coordination number of 6. And then when you get all the way up to maybe equal size, right, you're looking at a coordination number of 8. And the cases here where we have 4 and 6, right, these we've seen before. We have a tetrahedral interstitial and an octahedral interstitial, and these exist in the crystal structures that we have seen before. Okay, so let's talk about some of the crystal structures that are common in ceramic materials. The first is when you have a singly ionized anion-cation, right? So you would have this AX general format, an example of which is sodium chloride. And here you can make use of some of our earlier crystal structure studies and think of this as two interpenetrating FCC lattices. You have an FCC lattice of anions and cations, and they're just offset by 1/2 of the unit cell. You could also think of it as one FCC lattice, but at every position you have a 2-atom basis, right? One anion and cation. This works well for sodium chloride because of the ratio of sizes, right? If you look at, say, pick one cation, you can see that you have an anion above, below, to the left, to the right, in front, and behind. That gives you a coordination number of 6 over with an octahedral arrangement. There's also cesium chloride. So here, the chlorine is larger, and so it takes the body-centered position. And yeah, this is an example. This is actually a figure of calcium chloride, but cesium chloride is similar, except that because this is a 1-to-1 ratio, it's actually going to fill every body-centered atomic position. For calcium fluoride, this example, you only need half as many calciums because they're +2, and so half of these body-centered positions will be empty. You have so zinc blend. That's crystal structure that I don't have a picture of here, but it's very similar to the diamond structure that we will, I think, see later in these notes, except that you have two different elements, typically a group 3 and a group 5, so you'll see this often in compound semiconductors that we'll talk about in the second half of the course. You can also have much more complicated crystal structures than you're accustomed to seeing in metals, and this mostly has to do with the fact that you can have, first of all, you have anions and cations. You can also have multiple anions or multiple cations that work together to provide charge neutrality. For instance, this structure here is a perovskite structure where you actually have two types of anions and two types of cations, and one type of anion that form a more complex crystal structure. You can kind of see elements of BCC and FCC, but with different elements in different atoms in different crystal locations there. Okay, so it's a kind of a quick overview of general ceramic structures. We'll focus on here a couple of key groups. So first you have the silicates. This is SiO2 based, and in silicates you generally don't think about individual atoms as much as the unit, kind of the silicate unit, and that's SiO4, right? So if we remember, right, silicon is group 4, oxygen is group 2, and so you have 4 bonds to the silicon, 2 pairs, 1 electron from each. That actually gives you oxygen has extra electrons left over, so this is negatively charged kind of structure, and so it wants to bond to other SiO4 units nearby, which can give you a larger long-range ordered structure. If they form in a crystalline lattice, depicted here, where you have this is kind of a diamond structure where you have these tetrahedrals at every corner, as opposed to a pure carbon lattice. You've got silicate tetrahedrals. You can form quartz, which is crystalline silicon. If you don't have that long-range order, you would still generally have the same local bonding, but no long-range crystalline order. This would be indicative of silica glass, which has this amorphous structure. And the nature of that structure can be modified through the addition of other anions, such as sodium, right? These are called network formers because they modify the amorphous network that develops. You can have more complex silicates. Obviously, an example here is Mg2SiO4, and oftentimes these more complex structures will actually form in layers, where you have your different atomic groups, forming a layered structure. Okay. In addition to the silicates, diamond or carbon allotropes are common. The first that we should be familiar with is diamond. Here, this is similar to the zinc blende structure, or there's similarities also to the crystalline silicate structure, where you have at every corner you have a tetrahedral. The difference here is that it's made up of 4 carbon atoms instead of a silicon, or 5 carbon atoms, I guess, instead of a silicon and 4 oxygen, or a combination of group 3 and group 5. This is all group 4, and so carbon bonds this way to form diamond. And so you have this in carbon, right? The valence electrons of carbon, you have 2s2, 2p2. One of those s electrons gets promoted to become a p, so you have a more stable electron configuration of sp3, and then they all hybridize to get 4 equal bonds. That's how you form the tetrahedral. And then when they bond in this structure, right, you have a very tightly bonded crystal structure, which leads it to be very hard, with a very high melting point, and gives it a, we haven't talked about so much in this class, but a very large band gap. And so this large band gap, if you remember, so we've talked a little bit about this more for those of you who've had materials 560, but when we talked about electronic materials, we touched on it in materials 680. This is the energy gap that an electron must traverse to go from a stationary valence position in an atom to the conduction band, where it's able to move around the crystal. This forbidden energy region in diamond is exceptionally wide, which leads to very low conductivity because very few of those electrons can actually make it into that conduction band. It also makes them transparent because visible light does not have enough energy to excite those electrons into the conduction band either, and so it passes right through. Diamond can be obviously mined or grown in bulk, and also in thin films, which have many industrial applications. Diamond can also, so carbon can also form sp2 hybridized bonds, and in this case you get a hexagonal layer, and in these layers you have strong covalent bonds within the layer, but between them, because they're just sp2 hybridized and they form bonds to 3 neighboring atoms, the bonds in between are not covalent bonds, but they are van der Waals bonding, which, as we know, are weak. And so when carbon forms graphite, you get a different band structure, and this weak bonding here enables these layers to slide very easily next to one another, and so it gives you totally different properties from diamond. So graphite is much more conductive, both thermally and electrically, because the difference in this and the bond type and the arrangement of the atoms modifies the electron band structure, right, which makes the band gap not nearly as high, and so you get a good combination here of high conductivity and actually also lubrication. And so if you've ever taken apart like a motor or changed the brushes in a motor, graphite is used to make those brushes that provide lubrication and also high conductivity. A more recent discovery of carbon structure is shown here. This is a C60 buckyball, or a Buckminster fullerene, named after the guy who theorized it. And this is a stable spherical molecule, kind of a cluster made of 60 carbon atoms. And these fullerenes can exist on their own. They can also crystallize, and I believe they form an FCC lattice, which makes sense because, again, you have spherical particles packing in as densely as possible, and we know from our metals discussion that FCC structure is a common one for non-directional spherical particles that pack in densely. We also, in addition to fullerenes, we also have carbon nanotubes. That's very similar, if you can imagine kind of this structure only elongated in one dimension, where these hexagonal or graphite layer rolled up into a tube. That's what you get with a carbon nanotube. Okay, so we have those two major classes of ceramic materials. Now here's where we're going to see a lot of similarities between what we've talked about in metals. So in metals we talked about crystal structure and we talked about imperfections, and here, just like we did before, we're generally talking about the same kinds of imperfections, right? Vacancies and interstitials and impurities, substitutional impurities. Except here it's a bit different because of the requirement for maintaining charge neutrality. So if you have a one vacancy and missing one atom, right, that means that you have a charge imbalance. And so generally vacancies or interstitials occur in pairs. Two examples of types of crystalline defects are Frankel and Chpt defects. And the Frankel defect is shown here, and that would be where you would have, say, a cation that is vacant from its crystalline location, and that's because it's stuffed in with a neighboring cation, right? And so charge neutrality is maintained, but we have a vacancy here. We also have an interstitial of sorts. That would be contrasted with the Chpt defect, and in this case, you have essentially a double vacancy where you would be missing an anion and a cation simultaneously, which preserves the charge neutrality. Just like we saw before, we have a temperature dependence, right, shown in these for Frankel and Chpt defects. So there's going to be an activation energy associated with each of those. Generally, the activation energies are much higher because you are essentially having a double defect where you have a vacancy and an interstitial, or two vacancies, and so these are much higher. But then you're dividing by 2, which can help to offset some of that. Okay, just like before, you can have impurities. And remember, we did this in our homework, where large amounts of impurities occur for atoms that are very similar to the atoms that it's replacing, right? And so here it's going to be the same kind of thing, right? A similar size, a similar charge here. Charge is going to be really important. Can substitute for a given atom. Diffusion happens within the crystal, within a ceramic crystal, just the same. Very similar to metals. It's going to increase with temperature. It's going to be dependent upon how much space is present in your crystalline structure, but it's going to be more complex because now we're going to have charged particles moving through a charged crystal lattice, right? And so there's going to be repulsion and attraction, and it's not just a matter of random thermal motion solely. So the diffusion will be a little more complex. Similarly, another similarity that we see with metals is in phase diagrams. So these should look very familiar to the phase diagrams that we looked at previously. For instance, here we have alumina and I guess chromia, right? Al2O3 and Cr2O3. So we have similar cations, and we notice that we form a isomorphous solution, right? You can go from 0 to 100%. This is very similar to what we saw before with the copper-nickel phase diagram, and we see a very similar result here where you have the pure melting temperature of 100% one component and then 100% of the other component, and then a region where you have liquid and solid separating the solid solutions from the liquid part of the phase diagram. This is a simple one. If you've got a material system that doesn't have this similarity and this full solubility, then you have the introduction of different phases, different combinations of phases. Here you see similar structures where you have a eutectic point right here, right? This is a zirconia, I guess pure zirconium, and then you have this calcium oxide compound. But this looks a lot like the metal phase diagrams that we've seen. We have phases that can be very low solubility, and then we have the eutectic and eutectoid regions as well. And so as you heat these materials up to high temperatures, you're going to change the crystal structure, and then as you cool down, you're going to get solidification, and that can be accompanied by change in crystal structure, which, as we'll see, as I might mention a little bit later, can be challenging for ceramic materials in a way that it's not for metal materials because of the brittle nature. So if you have a significant change in crystal structure, that can come with a significant volumetric change, which can induce significant thermal stresses within the material, and because of its brittle nature, it can lead to cracking. Okay. Mechanical properties. So we've talked about brittle materials, right? Indicative of brittle materials is that you essentially have no plastic deformation. So if you look at a stress strain curve, you have elastic deformation and then fracture. So here's for aluminum oxide and for glass. The Young's modulus can differ, but essentially you have no plastic deformation. And because of their brittle nature, if you have a flaw, it can become a crack, and because you have no ability to deform at the front of that crack, you can't absorb that energy, and you have this runaway propagation of the crack, quickly leading to failure. So you can characterize the fracture toughness for ceramic materials just the same as you can for metals, except the values are going to be much, much lower. So much so that for ceramics you can have static fatigue. Remember, we talked about with metals, fatigue was generally a cyclic loading, right, where the load is applied and removed many, many times. With these ceramic materials, you can actually have a static load lead to fatigue over time, just due to the low fracture toughness. This also leads, unfortunately, to a large standard deviation in mechanical properties, because the strength is controlled by the propagation of cracks from flaws. You have a large standard deviation because there's a distribution of flaws within a material, and that leads to the direct difference in mechanical properties. So much so that you have bigger specimens actually of the same material being tested as being weaker, because when you have more volume of material, there's a higher probability that you're going to have a critical flaw present, or just more flaws present. As you have a smaller sample, you're going to have a larger standard deviation, because it's more likely that you could not have one of those critical flaws, in which case that would be significantly stronger. And in all these cases, generally with ceramic materials, they're much better in compression than they are in tension. since they are very susceptible to cracking. Compressive loads tend to force those cracks closed, whereas tension would tend to open them up. And so compressive loading minimizes the susceptibility mechanically of ceramic materials. And so this is why you generally see concrete pillars that are loaded in compression. Okay. From a fracture surface point of view, we talked about this a little bit in the mechanical testing regime, but you can look at the fracture surface of a crystalline material and identify, in many cases, where the crack began. So there'll be some sort of initiation site, and then radiating out from that, you have different regions with their different surface morphology. So you have this smooth mirror region here at the beginning, and then the transition to what is they call this mist region, and then this hackle region, and that's similar. Before we were looking at brittle fracture of metals, and we saw the chevrons that were pointing back to the initiation point, and this is a similar morphology. So I jumped down and talked a little bit about the stress strain, right? So we had no plastic deformation, and actually it can be difficult to do a stress strain curve, do a tensile test on a ceramic material because of its brittle nature. And so generally you don't generate these stress strain curves through a traditional tensile test. You actually do it through a bend test. So you would have a 2-point support and apply your force in the middle, and you're bending the material as opposed to pulling it apart. And you can extract the same elongation and stress from this data. You need a different formula. So here, if you have a rectangular versus a circular cross section, right, you have a different formula for the applied stress, and then you can measure the. I assume you would just measure the deflection, and that would be your surrogate for strain. But I've not actually done a test like this myself. Why is plastic deformation so low? Well, if you look at the crystalline structure for a ceramic material, they generally take crystal structures that have very few slip systems, right? So if we remember back to why metals are so ductile, right? It's because they tend to take FCC and BCC crystal structures that have very many parallel and intersecting slip systems. So it's easy for those atoms to slip relative to one another. For crystalline materials, they take different crystal structures that have fewer slip systems, and they also have to contend with repulsion of like charges. So as those atoms are moving relative to one another, they can actually be repelled from one another because of the like charges, which can either prevent them from moving at all or lead to the propagation of the cracks. For non-crystalline materials, you don't have slip. You have viscous flow, but the viscosity of these materials becomes very high at room temperature, and so they don't plastically deform either. Porosity is also a killer for mechanical strength. It sort of stands to reason that if you have a pore in a material, there's the possibility for a stress concentrator, first of all. And also, a pore is an empty space. It's a lack of material. And so you need the material to carry the load. And so, those kind of go hand in hand, because if you don't have the material, that's kind of like having a hole or a crack. And the stress needs to go around that pore. So it's concentrated. And as porosity increases, you see a decrease in strength. It can be quite dramatic here. You see in this expression here where you have the fracture strength for a for the fracture stress. You have, say, a nominal, fully dense sample, and as the porosity fraction, the volume fraction increases, right, you see an exponential drop off in that fracture stress. You can do hardness testing, although it's a little more difficult because of the brittle nature. And remember, hardness, when you're doing a hardness test, you're indenting the sample with some sort of a ball or a point, and you're producing plastic deformation, right? Well, ceramic materials don't plastically deform, so it can be more difficult to do a hardness test. Ceramic materials also creep. So if you take them up to high temperature, apply a static load, right, you will see that flow or that recovery that leads to elongation over time. But because ceramic materials tend to have higher melting temperatures, you see higher creep at higher temperatures as well. Okay, so that's, I believe, Chapter 12. Chapter 13 is applications and processing of ceramics. There is a similar approach here. There's a lot of different categories, and I'm just going to try to summarize and draw connections between the two. You have a helpful diagram here that kind of puts them in different classes, and we'll go through them one at a time. So glasses are generally non-crystalline, so we're talking about amorphous materials here. They are usually silicate based, and so the silica bond between silicon and oxygen has, again, a large band gap, and so these are transparent. And because they're amorphous, right, they, as we'll see later in the processing section, they become viscous at higher temperatures and are easy to change their shape and to fabricate. Glass ceramics are very similar, except that you get a crystallization at high temperature. So if you get a high enough temperature that the atoms can move around, then they can reform their bonds and form a crystalline structure. This is similar to what we've seen before, right? When we're forming crystals grow through nucleation and growth, and so the glass ceramics are going to have a very similar type of crystal growth that we are familiar with metals. They just happen at higher temperatures. So here, if we remember, for steel, the eutectic is at 730, 40-ish. Here we're looking at glass forming at several hundred degrees warmer than that. But we see this time temperature transformation curve here that looks very similar to where we have up here, instead of having, say, an austenite region, you just have a glass region. So there's enough thermal energy that you have disrupted the crystal structure, but as you cool it down, you have a temperature where you start to crystallize, and then it would be complete. You'd have the glass ceramic. Again, you see the nose of this curve here, where if you can reach a critical cooling rate, you can actually maintain, keep that crystal structure. And the time scale, I would point out here, is quite a bit different. If you recall, for metals, especially for plain steel, this curve was really fast, like at a second or so. Here, right, you have a much lower cooling rate required, right, on the order of maybe 100 degrees per minute as opposed to 100 degrees per second. That can be, makes it sound easier than it is, because remember, these materials are not highly conducting. Okay, so you have glasses, both amorphous and ceramic, and then you have your clays. Clays, from the very beginning of this course, I talked about natural materials versus man-made materials and the role of processing to improve the properties. Well, clay is one of those things that has existed um, since, say, prehistoric time. It's super easy to use. You can basically just dig it out of a riverbank and fire it in a primitive oven, and you can get clay pottery. Today it's still used industrially for bricks and tiles and pipes. You also have more refined clays that are fired at higher temperatures to form porcelain or china. Refractories is a class of ceramic materials that is characterized by extremely high melting points and inactivity or low chemical reactivities, which makes them great materials for the linings of furnaces, right? Because you want them to hold up to the high temperatures. You also don't want them to react with the chemistry that you are doing inside of the furnace. And so to keep that heat in, right, or to keep the material together, right, it needs to have binders. And also here's an application where a high degree of porosity, since this is non-load bearing, is desirable for the purposes of insulation. Okay. And okay, some examples of refractories. You've got fire clay, which is a high percentage of aluminum, Al2O3, silica-based refractories, and I guess basic, and then you'd have these special refractories, which are more pure, lower porosity, and more expensive. Let's see. Your fourth class of ceramic materials are your abrasives. So here, hardness is paramount because the idea is that it's abrasive to other materials. So it's got to be it's got to be harder, and which gives it wear resistance. So these abrasives are useful for making grinding wheels and sandpaper, and generally they would be made of silicon carbide, tungsten carbide, aluminum oxide, or silicon oxide, and the hardness of these dictate the applications that you would use them for. Lastly, you have your well, I guess second to last, your cements. So here, cement is this should be lime. Your Portland cement, plaster of Paris, lime, and the distinction here is that they are solidified not through crystallization or reduction in viscosity. It is a chemical reaction. So you have hydration reactions that occur at room temperature with water between the cement, Portland cement, clay, lime, and you form a bonding, a network of these water molecules that hold the material together. Okay, advanced ceramics, kind of a niche category. Here, the Callister gives a couple of examples. These are, high value, low volume type applications, especially for MEMS, micro electromechanical systems. I know many of you, several of you, are much more familiar with this than I am. But this is using silicon and other ceramic materials like silicon oxide and silicon nitride to etch and use photolithography. So here's kind of where you have an overlap a bit of the first and second half of the material, because we'll be talking about microelectronic fabrication and discussing a lot of the techniques that are used to make these MEMS systems. But advanced, high-tech ceramics, in addition to the MEMS, you also have optical fibers. So here, these are silica glass fibers, very, very thin, talking, say, 10 to 100 microns in diameter, so, thinner than a hair. And these are high-purity silica. So it's been purified of impurity, and the impurities have been removed to reduce scattering, because these are used for long-distance optical transmission. And then you can take advantage of ceramic hardness here. One application Callister mentions is ball bearings made of silicon nitride, which have a longer lifetime than steel ball bearings. Okay, I've got 2 more pages. I might go a little bit over 50 minutes. The last category, or the last topic, I believe, is this fabrication and processing. And so, like we saw before, right, the fabrication methods that are amenable to this class of material come directly out of its properties. So what we saw before was, for the metals, was there was kind of 2 basic categories of processing, and that was casting and forging. And you can't do either of those with ceramic materials. Casting is difficult because the melting points are very high, and for metals, a lot of times the crucibles that you would melt something in would be made of these ceramic materials, right? So if you want to melt the thing the crucible is made out of, what do you melt it in? You also can't form these materials because they're too brittle. And so the fabrication and processing kind of falls in a couple categories here, where you've got powders that are dried, mixed together, and then fired. Those are your clays. You would have materials that increase viscosity at higher temperature, allowing them to be formed. These would be your glasses, and then you've got chemical hardening, which I've already talked a little bit about, and those are your cements. During fabrication, you can have differences in crystalline versus non-crystalline materials. One big thing here is that if you have a crystallization, that is associated with a volume reduction. Remember, you're going from amorphous to a crystalline structure, right? And so generally, in most cases, crystalline structures pack the atoms in more densely. And so as you crystallize, you should see a reduction in specific volume in most cases. Crystallization also happens at a definite temperature, right? So as you go from a liquid to a more viscous state, if you maintain a glass, right, you don't have a definite crystallization temperature. You may have a region over which you change the heat capacity or something, some other properties, right, that's associated with what's called a glass transition temperature, and that's kind of the transition where you go from a solid state to more of a viscous state, but you don't have a definite melting temperature. And so for viscous materials, for glasses, you have various temperature regimes and associated viscosities. So for these common glasses here, where you've got silica glass or soda lime glass, as you increase the temperature, the viscosity goes down. So here at lower temperatures, right, you've got viscosities, and we're talking, this is log scale, so we're orders of magnitude difference, where you would have say room temperature down here, where strain would be present and persistent. If you heat up to a few hundred degrees, then you can anneal the glass, right? So they're not flowing, but the kind of the atomic level strain can be relaxed somewhat. As you go up in temperature, right, you start to soften the material, and then you reach a working range where it's easily formed. So if you've ever seen glass blowers, they pull that glob of glass, out of the furnace, right, and they can shape it, make intricate glassware, and then they keep putting it back into the oven, right, because they're trying to maintain this working range material temperature, right. If you go too hot, right, then you just it becomes too the viscosity goes too low, and then you've melted it. Okay, so for glass forming, once you get to this working range, you can take a gob of this material in an industrial setting, not so much like an artisan. You would generally use a mold, and if you're going to make a glass jar or something, right, you can have various steps here where you have rough forming and then use compressed air to form the glass against the sides of the mold. There's also sheet forming, and this was one of the I guess great achievements of kind of the Industrial Revolution, was figuring out how to make really flat glass cheaply. Glass panes used to be made by hand here, and they were never really totally flat, so you get distortions. But flat glass is made actually by floating it on a super flat surface of a vat of liquid tin. And so you melt the glass, and then as it floats in this liquid tin, it becomes really flat, and then the viscosity increases as it's cooled down, and you can anneal it to get rid of any strain that formed during its solidification, and then you've got panes of glass. And so annealing is especially important for ceramic materials. Because any thermal stresses, in most cases, right, thermal stresses are bad because of the brittle nature of the material. For tempered glass, right, that thermal stress is actually used intentionally to increase the strength and the fracture toughness of glass. And the way that's done is to intentionally cool the surface rapidly, so you get rapid solidification of the surface layer, but the inside is still hot. And so you cool the surface rapidly, you fix the structure, and then it starts to cool down. And as that inner portion cools down, it actually pulls on the outer pre-solidified region, which puts it under compression. And so if you have a surface crack, there is kind of a residual compression at the surface due to this, two-staged cooling, and that residual compression tends to push that crack closed. And so tempered glass has a much higher fracture toughness. But if you do overcome that residual compression, if you've ever broken a piece of tempered glass, you release all of that compressive stress at once, and it tends to form like a million tiny little pieces as you release all of that compressive stress at once. The glass ceramics, as we saw, glass ceramics are made by allowing enough time for the glasses to crystallize, and so you need the right heat treatment to allow that to happen. Clay processing. So remember, clay is a collection of very small particles, and so with the addition of water, you get a thin film of water that coat the particles, right? And this kind of gives clay like a hydroplastic formability, right? So you can, like clay on a potter's wheel, they're continually dipping their fingers and adding water into the clay to maintain this thin film of water that makes it more formable. And clays, alumina, silica, right, are some of the most common elements on Earth, which make up most clay and soil particles. Um, and so when you're forming clay, you have this hydroplastic um, form that enables you to easily make the shape that you want. And then you have a stage of drying where you evaporate away that hydroplastic um, thin film of water, and so that fixes the particles where they are. But then you need to fire the material to have a real solid, durable part. And so firing is done at elevated temperatures, and it produces a degree of vitrification. So what that is when the surface of these particles um, or other agents that are mixed in get hot enough to flow, and they bond together all of these disparate particles. You can also bond, you might have a material that is too high at melting temperature and is difficult to vitrify and make solid through that method. In that case, you might use powder pressing, where you have you take a powder of the ceramic material that you're interested in, and you put it under either uniaxial or isostatic stress, right? So you put it under stress and you heat it, and you sinter these individual particles together in a similar way. I didn't grab the diagram for it, but the last processing method covered by Callister is tape casting. So this is used commonly in making electrical components, especially like lithium-ion batteries. The anodes and cathodes are spread out on thin sheets with tape casting, and the way this is done is you have kind of a hopper of your slurry of whatever you're trying to cast, and you have what's called the doctor blade, which is there's a good. I should have added the diagram, but it's a blade that maintains a very consistent, very thin gap between the sheet and this hopper of material. And as you pull the blade across the sample, across the sheet, right, you're depositing a very consistent, very thin layer of the material, and then it will later dry and form a thin tape. Okay, so this video is at 56 or 7 minutes, something like that. And so we've covered ceramic materials, both the differences and similarities from a structure standpoint, crystalline standpoint, and then some of the applications and processing. So next we'll be looking at polymers, and I guess I'll sign off for this video.